Welcome to the lecture on inverse functions. Today we're going to talk about inverse functions, and inverses undo each other. So when you see a function, for example this one here where we have -2, 1, 5, 4, 3, 1, and 6, 2, what we're going to do to make the inverse is we're going to swap the x's and the y's. That's what inverses do. They undo each other. So the inverse relation would look like the set 1, -2. I just swapped these x's and y's. In the next order pair, when I swap, this will become 4, 5. The next order pair when I swap gives me 1, 3. And the next ordered pair gives me 2, 6. So the basic idea between an inverse function is that it's going to swap your x's and y's. Now, not every function has an inverse function back. If you look at this example right here, this is not considered a function, the answer that we just got, because this ordered pair has an x value of 1, and this ordered pair has an x value of 1. So 1 is being sent to -2, and at the same time is being sent to 3, and that is the definition of something that is not a function. We don't want to use x values more than once. So in order for a relation to be a function, each x value can only be used once. If you're looking at a graph, what this would look like is two vertical points. You'd have a point at 1, -2 and 1, 3. And so if you could imagine drawing a vertical line, it would intersect this graph in 2 points. So that's called the vertical line test. If every vertical line intersects the graph at most once, then you have a function. If it intersects more than once, like our example up here, then we do not have a function. So this inverse relation up here is not a function. So how can you predict ahead of time? If you start off with a function, how can you predict if you're going to get an inverse function back again? So how we do that is what's in green here. In order for a function to have an inverse function, each y value can only be used once. Remember, for functions, each x value can only be used once. So in order for the inverse to be a function, each y can only be used once. And instead of a vertical line test, we're going to have a horizontal line test. The horizontal line test says if you look at a graph and every horizontal line intersects the graph of the function at most once, then the function will have an inverse, and it's called 1-to-1. 1-to-1 means that for every x value, there is one and only one y value. And we want functions to be 1-to-1 because if they're 1-to-1, then they will have an inverse function. Okay? So 1-to-1 means that all the x's should be unique and all the y's should be unique. So x's should not repeat and y's should not repeat. And if you have that happening, then you're going to get an inverse function. And that's what we want in this section of notes. So let's test this out. Here is a relation, and I want to know whether or not it is 1-to-1. So if you look here, all these x's only got used once, and all these y's only got used once, and they're all unique. So yes, this is considered 1-to-1. In the next example, all the x's only got used once, but the y value 4 got used twice. It got mapped from 3 and also from 4. So this would not be considered a 1-to-1 function, and so it would not have an inverse function. Okay, so that's what 1-to-1 means, that there's no inverse function. It might have an inverse relation, but it's not an inverse function. Okay, what about the next one here? Here you can see that 1 got used twice. And so not only is this not 1-to-1, it's also not a function. To be a function, each x value can only get used once. So this isn't even a function, therefore it can't even be 1-to-1. Okay? In the last example here, all we're given is a rule. So to figure out if this is 1-to-1 or not, you want to probably look at a graph of this. And this is just x squared that's been shifted up 2 units. So you know that x squared is a basic parabola, and if we shift it up 2 units, then it's a parabola that's now going to hit at y equals 2. So here's my graph of my function f, and to see if a graph is one-to-one, you can very easily use that horizontal line test. So if you imagine drawing a horizontal line through your graph, does it intersect more than once? And in this case, it does. So that means this function does not pass the horizontal line test, so that it is not one-to-one. And that's because it failed the horizontal line test. Okay? So real simple rule to use. You use the vertical line test to see if you are a function to begin with, and this is a function, but it does not have an inverse function because it failed the horizontal line test. Okay? So let's practice again here, determining if something is one-to-one, and then if it is, we're going to find out what its inverse function is. So in this function f, all we have are a set of points. So to see if it's one-to-one, we want to make sure that each x is unique and only gets used once, and each y is unique and only gets used once. So the x's are 1, 2, and 0. Each one got used once. And the y's are 3, 4, and negative 3. They only got used once. So yes, this is one-to-one. So if it's one-to-one, then it must have an inverse. And its inverse function we could write with this notation. F with a little minus 1, that stands for inverse. Doesn't mean exponent, it means inverse. And to get the actual inverse rule, or in this case ordered pairs, we remember just swap your x's and your y's. So the ordered pair 1, 3 becomes 3, 1. The ordered pair 2, 4 becomes 4, 2. And the ordered pair 0, negative 3 becomes negative 3, 0. Okay, so here's our inverse function. For the next example, G, all we're given is a set of dots, a set of ordered pairs on a graph. So to determine if this is going to be one-to-one, we can use that horizontal line test again. So if you draw a horizontal line through this first dot, it only intersects one dot at a time. So yes, this is one-to-one. Okay? Then to figure out what the inverse function is actually going to be, it's sometimes helpful here to figure out what these coordinates are. So this first dot over here on the left is at negative 1, 1. So in the inverse, when we swap that around, it becomes 1, negative 1, and would get graphed right here. So the inverse of this dot is this red dot. If we go to this dot up here on the y-axis, it has coordinates 0, 2, so that when we swap it, turns into 2, 0. So this point right here gets mapped to the point 2, 0 on the x-axis. And for the last black dot, this is at 3, 0. So when we swap that, it turns into 0, 3 and becomes this red dot up here. So the 3 red dots would be the inverse function G, G inverse. Alright, so that's how you find inverses if you're given ordered pairs. You just swap x's and y's. How do you find an inverse if you're given an actual formula for your function? And it's really the same idea. All we're going to do is swap x's and y's. So the first thing we want to do, here's our 5 steps, is verify that the function really is one-to-one so that we can find an inverse function. Once we have that it's one-to-one, then we're going to go through our steps of swapping x and y, and then solving for y so that we can change y to f inverse and label our new inverse function. So if we have f of x equals 2x plus 1, how could I verify first that this is a one-to-one function? Well, hopefully you know what the graph of this function is. It's a line because it's a linear function. And you can graph it very carefully if you want, or just do a rough sketch. This has a y-intercept of 1, this plus 1 on the end, and the 2, this coefficient of x, is your slope. So your slope is up 2 over 1, so roughly this line is going to look like that. So why is this graph one-to-one? Because it passes the horizontal line test, and therefore it's going to be a one-to-one function. So if it's one-to-one, then we know that it has an inverse. So how do you find it? Well, the first thing we're going to do is we're going to change f of x into y, so that we can think in terms of x's and y's instead of this function notation. So that's this step 2 right here, change f of x to y. The next step, we need to do the swap. To get an inverse, you need to swap your x's and your y's. So now I'm going to change this y into x and this x into y, and everything else will stay the same. Now this is actually your inverse right here, but to write it as an inverse function, you need to be able to solve this for y. So now we're going to solve for y, and to do that we want to isolate the y, so all I have to do is subtract 1. And then to solve for y further, we could divide by 2. Now you can divide the whole left side by 2, or you could divide x over 2 minus 1 over 2. You could do it separately. So I'm going to turn this around here and put the y first. Y is x minus 1 all over 2. And the very last thing you do is you label it with correct inverse function notation. So since the name of our function was f, then this new answer we got is going to be f inverse. So f with that little minus 1, and its rule is x minus 1 all divided by 2. Okay? So let's try that again over here. We have f of x equals 2x cubed minus 3. How do we know that this is one-to-one? Well, again, you probably would want to consider a graph of this, and if you don't really know the graph of x cubed very well, it looks kind of like this normally. It looks like a sort of a flat shape that rises pretty quickly, and then all these numbers 2 and minus 3 do is kind of shift it around a little bit. The minus 3 is going to lower it 3 units, and the 2 just kind of steepens it. It makes it have a little stretch. If you have a graphing calculator, you could help visualize that. But the 2 and the minus 3, those are not going to affect anything more than just the steepness of the graph and where it's positioned. Is this graph in red going to pass the horizontal line test? Yes. So that means this is going to be a one-to-one function. Okay, now that we know that our function has an inverse because it's one-to-one, we're going to go through our 5 different steps. We've already verified that it's one-to-one, so our next step is going to be to change our f of x to y. And then we want to do the all-important step of swapping our x's and our y's. So this becomes x equals 2y cubed minus 3. And then we want to solve this for y in terms of x. So if I want to get this y by itself, the first thing I'm going to do is get rid of this minus 3 that's off to the side. So I'm going to do that by adding 3 to both sides. And then to further isolate our y, I'm going to want to get rid of that coefficient of 2. So I'm going to divide the entire fraction on the left side by 2. And then finally, I want to undo the cube on our y. And what's it going to take to undo a cube? Well, the inverse of a cube is a cube root. So we're going to need to take a cube root of both sides, so that cube root and that cube cancel out. And what we end up with is y equals the cube root of x plus 3 all over 2. Or if we use our function notation and change this to f inverse of x, we get the cube root of the quantity x plus 3 all over 2. Okay, on the next couple of problems, we want to do kind of the same thing, graph our function and its inverse on the same set of axes. So we're going to want to find the inverse, but we're also going to want to graph what it looks like. So let's start with graphing the original function f of x here. So f of x equals 2x minus 3. You should know again that that's a line. It has a y-intercept of negative 3, and it has a slope of 2. So I go up 2 over 1, and this blue line here is going to be my graph of f. Now to graph the inverse, we need to know what the inverse should be. So we need to go through that process. Now I know that an inverse exists because this line passes that horizontal line test. So this is definitely a one-to-one function. So in order to find the inverse, what you do again is you first replace f of x with y, then you swap your x's and your y's, and then you need to solve this for y. So I'm going to add 3, and then I'm going to divide by 2. This time I'm going to divide each individual term by 2 because I want a graph here. And so if we get y by itself, and I'm just going to turn this around and put the y on the left, then we get x over 2 plus 3 over 2, which is the same as saying instead of x over 2, you can think of that as 1/2 x. That 2 in the bottom is like a coefficient of 1/2 out front. Why am I thinking of it this way? Well, if I replace this y with that inverse function notation, so f inverse of x, then this rule that we just ended up with, 1/2 x plus 3/2, is a line back again. It's a linear function, and the 3/2 is the b, so I can go to 3/2, which is 1.5, and put a dot on the x or the y-axis. And then that 1/2, the reason I wrote that 1/2 out front is because now I can think of that as my slope. From this dot, I'm going to go up 1 over 2. And so in red here is the graph of my f inverse. Okay, here's my graphs. One thing you want to notice is that whenever you graph a function and its inverse on the same axes, what you should always see is that the two lines are reflections of each other across the line y equals x. So if you could imagine folding this piece of paper diagonally across that line y equals x, what you get on one side of the line should be the same image on the other side of the line, so that they are reflections of each other. So you know you graphed this correctly if you can see that reflection. Okay? Let's try one more example like this. In this function here, we have f of x equals negative square root of x. So if we graph that, keep in mind one thing here for me a moment. When we graph square root of x, what is the domain of that function? What kind of x's am I allowed to use in this function? Because we have a square root, remember that when you graph, you can only graph real numbers, and that means I can't take the square root of any negative number because that's not a real number. So the domain of this function is only zeros or positives, so 0 to infinity. So if we do that, what kind of graph is this going to have? Well, normally square root of x starts at the origin, and then you go up 1 over 1 so that you go through the point 1, comma 1, and then you go up 1 over 3 so that you go through the point 4, comma 2. Normally that's what square root of x looks like. What does that minus do in front of it? That's called a reflection over the x-axis. So that's just going to take this normal square root graph and flip it upside down over that x-axis. So I'm going to erase this graph, and in its place I'm going to put the reflection. So 0, 0 doesn't move, but instead of going up 1 over 1, we're going to go down 1 over 1, and then down 1 over 3. So we get that same arcing shape, but now it's going below the x-axis. So that's what f of x equals to negative square root of x looks like. What's the range of that graph? So what y values does this graph go through? Because the arrow is pointing down, that means we're going to go all the way down to minus infinity, but we go no higher than 0. So this range is minus infinity to 0 with a bracket around the 0. Now I'm finding this domain and range because we're going to need to use that in just a minute. So there's my graph of f, and let's go ahead and see if we can figure out what the graph of the inverse is going to look like. We know that it exists because this is a one-to-one function. So in order to find the inverse function, we're going to replace f of x with y, and then we're going to swap our x's and our y's. And now to solve this for y, we want to kind of undo that square root, and we can undo a square root by squaring. So I'm going to square both sides. So the left side becomes x squared. On the right side, you're squaring the negative as well. So the negative squared goes away, and the square root squared goes away, and we just get y. And if we replace this y with that function notation, this is going to be f inverse of x equals x squared. Now, if you go to graph that, we know that x squared is a parabola centered at the origin. You go over 1 up 1 on the right, over 1 up 1 on the left, over 1 up 3 on the right, over 1 up 3 on the left. And so this is what the graph of x squared would look like. We know that something should be wrong here. Something's wrong because remember what I said earlier about reflections. A function and its inverse should be reflections across the line y equals x. And that is not the case here because this red graph has more pieces to it than the blue graph. So something's not quite right. Alright, so this is why we want to kind of consider domain and range. If you remember that the domain for the original function was 0 to infinity and the range was minus infinity to 0, and remember that functions and their inverses swap x's and y's, the domain is x's, the range is y's. So in the same idea, the domain and the range of the inverse are going to be the swaps of the domain and range of the original function. So the domain of the original function f becomes the range. So 0 to infinity should be the range of our inverse function, and the range of the original function becomes the domain of our inverse. What does that mean in terms of our graph here? Well, if we say that the domain needs to be minus infinity to 0 only, then that's not both halves of this parabola. Which part of this parabola has as its domain minus infinity to 0? Those are negative x's. So the only part of this parabola that we're supposed to keep is the left half right here, because the right half isn't going to use the correct domain. So we actually want to erase the right half of that parabola, and then when we look at our reflection, this does look correct. If I fold along that diagonal line, the blue graph will map directly onto that red graph. So here we kind of had to restrict our domain so that this would be correct. And the easiest thing to remember here is, since inverses swap x's and y's, they also swap domains and ranges. So if you know the domain and range of your original function, then you also know the domain and range of your inverse as well. Just swap them. Okay? Alright, let's try two last examples here. So in the next example here, we have this new function f, and the only thing we know about f is that f of 3 is equal to 6. What we want to know is what then must f inverse of 6 equal. So think about this function notation. If we know that f of 3 is 6, then that means that f takes 3 and sends it to 6. Or in other words, the ordered pair 3, 6 is on the graph of f. If that's the case, then what do we know about the inverse function? The inverse swaps x's and y's. So if f sends 3 to 6, then the inverse must send 6 back to 3, or in other words, the ordered pair 6, 3 is on the graph of f inverse. So what is f inverse of 6? Well, since f inverse sends 6 to 3, then this must equal to 3. Okay? So even though we didn't know anything much about our function, we were still able to answer the question because we know about this inverse relationship. Okay? In the same idea on this last example, all we know about our function is that it consists of these 4 dots, and we want to find f inverse of 4. Now this time I'm not telling you anything right out, just like in the last example, that f of 3 equals 6, so it's not quite as obvious maybe as the last problem. So here, if we think about this, what we want is to find out what f inverse sends 4 to. We want to know what f inverse of 4 is. So what does it send 4 to? Well, if we don't know, think in terms of the inverse. This graph here is the graph of the original function f. So if I can look at the graph of f, what should I be looking for? Because of this inverse relationship, 4 gets sent to something on f inverse, so that same something needs to get sent to 4 on the original function f. These are your x values, these are your y values. So on the graph of f, we want to be looking for a y value of 4. So which of these dots has a y value that's equal to 4? Well, y equals to 4 would be along this horizontal line, and the only dot that hits y equals 4 is this dot right here. And it has the ordered pair -1, 4. So that means on the graph of f, -1 got sent to 4, therefore on f inverse, 4 gets sent back to -1. So the value of f inverse of 4 must be -1. So it's really the same problem as the last one we did, but you're looking at ordered pairs and dots on a graph instead of being given the value in a function notation. Okay, so that concludes our notes on inverse functions. Good luck.